So thank you so much. Merci, mille fois. Greetings from Norway, and my company, as I flew here, changed its name. So the energy giant Statoil is now the energy giant Equinor. Equi stands for equilibrium, equality in society, and the Nor is our Norwegian heritage. And our CEO is very clear is that he wants us to be a broad energy company. So times are changing. Today I will tell you about our CO2 storage technology, and it's a pleasure to be here. A lot of people have stressed the importance of what we're doing, but ultimately CO2 storage technology is about keeping greenhouse gases in the ground. And many have already alluded to it, but the big question is, can we go low carbon? Can we deliver on the Paris Agreement? And I would say very simply, we have to. We know how to. And it will need CCS technology. And it's not just the big energy companies that are saying this, it's the leading scientists on global climate change that are saying this. So this is a unanimous agreement. We have to do CCS. And to my mind, it's all about protecting the atmosphere. This image from one of our famous astronauts from the International Space Station shows you how thin and fragile the atmosphere is. So the business case for carbon sequestration and storage is protection of the atmosphere, in my opinion. Renewable energy is essential and very attractive, and it's a key part of the low-carbon energy mix. Everybody likes it. Doesn't that picture look lovely? And Equinor is actively working on offshore wind power, one of the leaders, and we have been developing a deep water turbine that will take offshore wind into really global expansion, and the capacity there is huge. But whenever you look at any of the renewable options, solar, geothermal, wind, hydrogen storage, etc., it just does not do the job enough for the Paris Climate Agreement. Globally, we are still increasing emissions. We have leveled off, but we have not reduced emissions. So the only way to reduce emissions is to capture CO2 from power generation and industry and to store that CO2 in the subsurface, which is what I will talk about. The problem with the carbon capture, utilization, and storage industries is that they are essential, but they are unattractive. They are unattractive to politicians, they are unattractive to business because there is no business driver, and they are unattractive to society because they are suspicious and they don't like the investment. And there's a dilemma. Fortunately, Norway has been pushing and leading this technology for over 20 years now. We started the Sleipner project in 1996. We then followed that with the Snøhvit CCS project in 2008. We launched the world's largest CO2 capture test center near north of Bergen in 2012, and currently the Norwegian government has signaled its intention to proceed with a large CCS value chain project, which is in the design stage right now, and I'll tell you a little bit about that. So it's a good track record, 22 years of operations. We're building confidence in the CCS process, and I know the researchers who are involved in all the different elements of that are very pleased to see some industrial progress. But it's still not enough. Although we are capturing probably 10% of Norwegian emissions, we are only capturing 0.01% of European emissions. Okay, so there is a huge amount of work to go. The scale-up is enormous, and the scale-up is necessary. In case you don't know, the Sleipner project, we produce natural gas from a deep layer. It contains around 9% CO2. We process that CO2 using conventional amine technology on the platform, and we re-inject the CO2 in a shallower rock formation called the Utsira. The business case from industry for the capture part is we can't sell the gas without removing the CO2, so that pays for the capture. The business case for storing it in the ground is the Norwegian government will tax us if we throw CO2 into the atmosphere. So we have a €50 per ton surcharge for emissions to atmosphere, and that is why the Norwegian industry is driving hard to get these emissions down in the petroleum sector. Part of the gas field development, conventional amine capture, 0.9 million tons per year, and we started in 1996. The other important part of this project is the longevity of it. It demonstrates the technology works, but in detail, it tells us more details about it. I was asked to do a little bit of the easy stuff. What happens when you capture CO2? It's compressed and injected underground in the dense form, and Professor Laulu explained that very well. And an important point here, on the right was the density diagram. We go from the gaseous phase at the surface to a liquid phase in the deeper levels. And these deeper levels, about 800 meters or below, around a kilometer, are also the levels at which we know natural gases have been stored for millions of years. So from an empirical argument, CO2 storage, similar to gas storage, we know should be safe at these depths. But it requires some energy. The compression ratio is about 100 to 1, and the volume ratio from the surface CO2 to the subsurface CO2 is about 365 days to 1. So it's a nice number to remember. 365 footballs squeezed into 1 is the volume ratio that we involve. And to do that, it requires a series of gas compressors, and it requires good engineering of your injection devices. And I just show you this diagram of the CO2 injection well at Sleipner. There are many components of the wellhead engineering. It's a long-reach horizontal well to take the CO2 away from the platform. And the components of the well include very high-quality, high-chromium carbon steel for the exposed members, and that is a very expensive component of the well. So overall, this well is more expensive than conventional wells because we've chosen very non-corrosive components of the well. But look how successful that was. This well has delivered constant CO2 storage at around 1 million tons per year for 22 years. The only problem we had was in the first year of operation when we had to recomplete the perforation at the wellhead, at the well foot, to achieve better injectivity. So it demonstrates two things, that it works, but in particular it demonstrates the value of careful engineering design. On the subsurface, which is kind of my home territory, this is a nice sort of summary schematic of where we're injecting the CO2 with this long-reach horizontal well into this 200-meter thick Utsira formation, a very high porosity, high permeability sandstone, so it should be good. And the image on the top from the seismic is the top structure of the Utsira formation, and you can see here the injection point and two geological structural closures or anticlines, which we hope the CO2 will stay within. How do we assure that the CO2 is staying there? And that's the big question we get asked all the time. And the main method we use is time-lapse seismic imaging, which in terms of physics is very complicated. But when you introduce CO2 into a sandstone layer, you change the acoustic impedance or the seismic reflectivity of the layer, and you also change the velocity of the path. So we use both time delay analysis and amplitude change analysis. And this very nice graphic shows you our best attempt at showing you where the CO2 plume is from time-lapse geophysical data. And you can see it's multi-layer, and it's now reached the top layer, the 9th layer, and it's filling the first structural enclosure, and it's moving to the second structural enclosure. But overall, what this ensures us is that the CO2 is staying where we expect it to be. The size of the plume is about 3 kilometers, and for the long-term integrity of the site, we have to assure our regulator that we know where the CO2 is and it's not going to go beyond the design criteria. And in Norway, we have now implemented the EU directive on CO2 storage. So since 2015, this site is now compliant with the EU law on CO2 storage, which is now implemented into Norwegian law because we're also not fully part of the European Union. So this demonstrates the value of geophysical monitoring, and it assures us and our authorities that we have containment of the CO2. The second project, Snøhvit, in the north of Norway, is interesting because it's combining CO2 capture with a LNG plant. Otherwise, it's similar. We're taking CO2 from the natural gas, separating it, and then re-injecting it in the oil field. But this time, the oil field is in deep water, 300 meters, so all the technology is subsea technology, which is quite important for the emerging project, which I'll tell you in a minute. And you could say that the Snøhvit project has lower permeability and a little bit more challenging in terms of pressure. And that was an interesting analysis of what happens when you raise the pressure of the rock formation. Will it fracture? Will it cause micro-earthquakes? Basically what happened in Snøhvit is we had a gradual rising pressure trend. Part of it was due to chemical effects, which we solved in the operational part, but this long-term trend was due to the geological containment barriers. So we put in a well operation in here, quite expensive, and then changed the injection plan, and then we're now injecting into a different layer where the pressure is equilibrating very well and the injection is going fine. So basically, we had an operational challenge. In terms of oil engineering, these challenges are completely normal. But when it comes to CO2 storage, the amount of interest in these challenges is very high. So the public interest in this was very high in the Norwegian papers and globally. And our early injection in this fluvial deltaic reservoir, which had the barriers, was then replaced by injection in another layer and went very well. And that basically shows you the importance of the flexibility of the well design. You cannot design a good well that will function, for 20, 30 years without having some flexibility. And a key part of the flexibility here was the ability to inject in different layers and decide to change that injection plan as the injection proceeded. And when we're looking at the risk of future projects, that flexibility will be very important. Finally, my little public explanation of science. So we get asked all the time, is CO2 storage safe? And I think you asked for it now. And there are lots of aspects to that. I've stressed the engineering, there's also the understanding of the geology, and there's ultimately understanding physics. But it's surprising how many people misunderstand what's happening. So I used this aquarium experiment, which I've showed to kings, to queens, to CEOs, to sheikhs, and to lots and lots of school kids. And I hope it's not too junior for you. What I'm going to do, my capture is an aquarium pump, which I bought in the fish shop, and the tank I made, and then there's a food sieve. I'm injecting some air through my little tank, through my little pump, through a pipe in here into the sieve. And as I bubble the air into the food sieve, and the food sieve has apertures of 1 millimeter, you can see that the air is stored safely beneath that dome-shaped food sieve, okay? Now, the engineering part is that as long as we don't allow the pressure in that accumulated air column to exceed the threshold pressure of that particular food sieve, that CO2 will stay there forever. It won't leak at all. So as long as I stop injection before the threshold pressure of the food sieve, there is no leakage. Not ever. Not even a little bit. Because of a capillary seal. And this is actually a nanochemistry effect, which we know well about in science, but somehow it doesn't communicate to the population. And that's why we have oil and gas reservoirs in the deep subsurface. It's the same phenomenon. If we move to a little bit more high science, here is some very recent imaging of CO2 at the pore scale, at the sort of micrometer scale, in a real pore rock system. Some simulations produced by Imperial College and Sam Creever. And we can look also at the dynamics of that CO2 in the pore space, and you can see a little bit of oscillating between the snap-off of the grains in there. But ultimately, that is the reason why CO2 stays in the subsurface. It is trapped by capillary forces. So that is ultimately why CO2 storage is safe. It's a matter of physics. There's a bit of engineering, there's a bit of geology, certainly, and it's a complex problem, but ultimately, we know the fluid physics works. And in the last few minutes, the future project, we're currently working on this large Norwegian CCS demonstration project. Equinor, Shell, and Total now work together on the storage part of this. It's a government-led project by the Norwegian government. It has 3 capture plants in the Oslo area, connecting by ship transport to a storage site of Western Norway, and the storage site which we're focusing on will take captured CO2 from an intermediate storage set of domes, and then pipe them via pipeline to an offshore template, which is very like the Snøhvit project, which we've operated for a decade now. The Norwegian government 2 days ago announced they're continuing with this project, which is very important because it's dependent on government funding. They've actually slightly scaled down the capture part in that they've decided not to prioritize the ammonia plant at Porsgrunn, but they will carry on with the cement factory and the recycling plant. And the Norwegian philosophy is to focus now on industrial capture and storage. And I do not speak for the Norwegian government, but I know that the other thing that the Norwegian government is very keen is to get partnerships for this project, both with the other European nations and with industry. So you're very welcome to join. The point about this project is it should continue to reduce the risk and the threshold for new projects, and it should enable large-scale CO2 storage should Europe decide to bury its CO2 emissions, which it currently is not doing. It could allow stepwise development of CCS hubs, which we're very pleased. We're working with the Netherlands and the UK on emerging projects, which is good. And it should form the basis for what we'd call emerging CO2 value chains. There could eventually be enhanced oil recovery with CO2, which will provide an economic boost. And there is a lot of focus now on natural gas to hydrogen. If there is a hydrogen economy in Europe, then we would use the North Sea oil field area as the disposal site for the CO2 separated from natural gas. So we hope, and we continue to hope, that Norway will continue to be a catalyst for rollout of CCS in Europe. And I hope I've persuaded you how important it is to do CCS. You simply cannot ignore it. Thank you.
Yes. Good morning, Alexandre Bouchet from Energy Centre, EPFL. Quick question regarding CCS. Do the CO2 emissions captured compensate for the emissions linked to the energy invested to compress CO2? And if so, what is the return ratio so far in terms of net CO2 emissions captured?
Yes, I mean, and that is an important question. It's the penalty, the energy penalty for the capture and compression process is between 15 and 20%, okay? At Sleipner, we capture all the CO2 from the natural gas, so the efficiency there is 99.9%, but the energy penalty, to add to it, we have emissions, and of course we use gas-fired power generation to run the plant. And the emissions from the gas plant to run it are not captured. So that if we wanted to go 99% on the whole process, the life cycle process, we would need green energy to run the plant, and then we would be up to 99% efficiency.
I'm Bernard Blaise from NG Group. You mentioned very rapidly the issue of the business model of CCS, and you detailed some. You mentioned some subsidies that could be given. Can you give some insight about the cost of this and the return on this on investment of this large capex?
It's a very hard question to answer, but I'll give you the very simple one. These two projects I mentioned are cost effective with €50 per ton tax of CO2. And they are natural gas processing, which is cheaper than, if you like, power plant capture. And if you were to go to power plant capture, you're going up to well beyond €100 per ton. So that's really the present gap. So right now in Norway, €50 per ton makes these two projects self-economic, okay? But if you were to do large-scale capture from industry and power sources in general, you're talking 100 plus, and it's a very complex answer.
Thank you very much. I propose a big round of applause for our panelists.